Let us now talk about trie representation and its internal working. Here are trie node representations in C++ and Java. This is a C++ structure that represents a trie node, and this is a Java class that represents a trie node. In these representation, I have assumed a very simple implementation. I am assuming that my dictionary contains only lowercase English alphabets, right? So I've made arrays of size 26 in both the implementations. If we wish to handle larger size alphabet, for example, if we wish to handle all 256 characters in C++, we can either make an array of size 256, and if we wish to optimize the space, we can use an unordered map. In Java, if we wish to handle all Unicode characters, we can again use a hash map, where our character represents the key and node reference represents the value. In a trie node, with the children, there is one more field, Boolean isEnd, which indicates whether this node is end of a word or not. And then we have a constructor in C++ which initializes isEnd as a false and initializes all the 26 children as null. In Java, we do not need to write such a constructor because isEnd will automatically be initialized as false by the default constructor, and 26 children references will also be initialized null by default. So every trie node has two things. One, an array of children, which is 26 sized array, because we are assuming lowercase English alphabets A to Z and their corresponding values as 0 to 25, which are used as an index in this array. And a field isEnd, which is initialized as false. See, if I want to know the particular child corresponding to any character, suppose I want to know the child corresponding to character C, what I'll do is I'll take C's ASCII value and I'll subtract A's ASCII value. What will I get? I'll get 2, right? So I'll go to index 2 to know the child corresponding to character C, right? So I'll take the current character's ASCII value, subtract A's ASCII value from it, and I'll get the index of particular child corresponding to that character, because ASCII values are contiguous. This has ASCII value 97 and then 98, then 99. So I'll subtract 97 from 99 and I'll get the value 2, and I'll know that this C corresponds to the child corresponding to index 2, right? And B corresponds to child corresponding to index 1. So this child is for A, this is for B, and the last one is for Z. Now we understand internal representation of every node. This is how they are internally represented. Let us insert all these keys one by one into an empty trie. Please note that an empty trie is represented by a root node with all 26 children as null and isEnd as false. And this representation is different from binary tree. In binary tree, we represent an empty binary tree as null. We do not allocate any memory for root in binary tree. Here we have memory allocated for the root even in an empty trie. It is just that all the 26 children are null for this root and isEnd is false. Now let's insert BAD. So when we insert BAD, we begin with the first character of this particular string or word, and we begin with root. And every node that we visit, we check whether there is a child corresponding to this character or not. So do we have a child in root for character B? See, initially all 26 children are null, so there is nothing for character B. So what are we going to do? We are going to create a new node, right? And we are going to link it with this particular index in the root, right? So this is not going to be null now. This is going to have the address or reference of this particular node. So we link it with this B. And this is also false for this. Now we go to the next character in this string and go to the next particular node in the trie. We begin with root and then go to the next level that we have just created. Now we see, do we have a child corresponding to A in this particular node? All the 26 children are initially null, so we do not have anything corresponding to A. So we create a new node for the child A. We have it as false initially, isEnd is false. right? And we now store the address or reference of this node in the child array of this particular node at this index, right? Because this is for A. Now we come to the next character D and we check, do we have a child for D in this particular node? We do not have. So we create a child, we create a node with initial default values and have reference or pointer of this node and child of this particular node. So we have D here. And this is the last character of this string. So we are going to have is and as true. Please note that is and stores whether this particular character or this particular node is last character of a particular word. So D is a last character of a word. So we have is and as true. So it helps us in searching. When we are searching for BAD, if we stop at a node which is having is and as true, we know that this word is present because we have reached the last character of string and we have reached a node with is and as true. Let us now see how do we insert BAT. So we again begin with the first character of our string and we begin with the root. We check, do we have a child corresponding to character B in this particular root node? We have a child. So we go to the child and we go to the next character of the string. Now we check, do we have a child corresponding to character A? We have a child. So we go to the child and we go to the next character in this string. Our next character is T. And now we check, does this node contain any child corresponding to T? It is having value as null in the child array for T. It has only one value as not null for D. So we create a new child node for T. Right? And we have initially this value as false. And we link it with the parent by storing the address or reference of this particular node in this child array of this particular node. And we mark this as true because this is end of a word in this particular string. Let us now insert next word GEK. So we begin with the first character of this word and we begin with the root and we check, do we have a child corresponding to G? We have only one not null child B. So we do not have anything for G. We create a new node. We initialize its isn't as false and we link it with the parent by storing its pointer or reference in this particular array of parent. Now we go to the next character E and we come to this node. We know that there is no child corresponding to E. So we create a new node and we link it. We initially have false for this E. Now we come to the next character E and we do not have any child for E. So we create a new node and we link it. We have it as false. Now we come to the next character K and we know that we do not have any child for K. So we create a new node and we link it. So we are going to have false for this. And this is for K. Now this is last character of this particular word. So we are going to mark it as true. Now we go to the next word. Let's insert GEKAS. So we begin with the first character and we begin with the root node. We have a child corresponding to G, right? So we go to the child and we go to the next character. We have a child corresponding to E. So we go to the child and go to the next character. We have a child corresponding to E again. So we go to the child and go to the next character. We have a child corresponding to K. So we go to the child and we go to the next character. And we look for S in this particular node. We do not have a child corresponding to S. So we are going to create a new child and we are going to link it with the parent. And this time for this particular child, we are going to have this value as true. Right? And this child corresponds to S. Right? So this is how we insert GEKS. Let us now insert the next word, CAT. So we begin with the first character C and we begin with the root node. We check that we do not have a child in the root node for character C. So we create a new child for character C and we have this value as false. Now we go to the next character A and we do not have a child in this particular node for A. So we create a new child and we have it as false. We go to the next character T and we check, do we have a child corresponding to that character in this? No, because it has all 26 as null. So we create a new node, and this particular field is and is going to be true in this node because this is end of a word. So this is how we insert CAT. Cat is inserted. We have marked the last character as true. Now we are going to insert cut. So when we insert cut, we begin with the first character, we begin with the root node. And we have a child already for C. So we are going to come to here and we are going to the next character of the word. Do we have a child for U? We do not have a child for U. So we are going to create a new node and we are going to link it with this particular node. So we are going to have a new child for U and we are going to have its address or reference in its parent, and it's going to be false. Now we come to the next character T and we check, do we have a child in this for T? We do not have a child. So we are going to create a new node, right? And we are going to have this as true because this is end of the word and we are going to link it with the parent. So this also corresponds to T. Now we insert the next word Z00zoo. So we begin with the root node. We begin with the character Z. We do not have a child for Z. So we are going to create a new child for Z. And we are going to have this as false. Now we come to O and we come to this particular child. We do not have a child in this node for O. So we create a child of this for O and we mark it as false. Now we come to the next character here and we come to this node. We do not have a child for O. So we create a child and we mark it as true because this is end of a word. So this is how this zoo is also inserted in this trie. We have talked about trie insert. We have created this trie for this dictionary. Let us now talk about search operation. How does search work? Let us try searching different words in this created dictionary using trie data structure. So let's see how does the search for BAD works. We always begin with the root and we begin with the first character of the string that we are searching. So we are searching for BAD, we begin with B and we begin with root. For every node, we check, do we have a child corresponding to the current character of the string? So do we have a child corresponding to B? We have a child. If we do not find the child, we immediately return false at that point only. So we have a child, we go to the child and now we go to the next character of the string. So we come to A and we check, do we have a child in this node for A? We have a child. So we go to the next character in the string D and we check, do we have a child for D? We have a child for D. Now there are no more characters in this particular string that we are searching. So we need to check the last node that we reached. Does it contain is end of word as true or not? It contains end of word as true. So we return true here. I have marked all the nodes here with is end of word as true explicitly using blue so that you can clearly see what are the nodes that have is end of word. Also one more thing, is end of word does not mean a leaf node. You can see this is not a leaf node and is end of word is true for this. Let's now search the next string GEEK. So we are going to begin with the first character of this and we are going to begin with the root. We have a child corresponding to G. So we'll come here, then we'll come to E, then we'll come to E, then we'll come to K. And when we come to K, we are here, right? Now we do not have any more characters and we see that the node at which we are now, it has is of end of word as true. So we return true. Let's now see how does search for GEE work. We begin with the root and first character of this particular string. So we come here, we have a child for G. We come here, we have a child for E. We come here, we have a child for E, right? And this is the last character of GE. Now we check, do we have is end of word as true for this or not? It is false. So we are not going to return true in this search. We are going to return false. So GE is not present. Let's see CATER. So we begin with the root, we begin with C, right? We have a child for C, we come to the child. Now we come to A and we come to the child. We have a child for A, we come to the child. Now we come to the next character, next node. So we have a child for T, right? Now we have visited T, we come to E. And we check, do we have a child for E in this particular node? We do not have a child. So we stop here because the child is null and we return false. So whenever you do not find a child for a character and you have not visited the whole string, then you simply return false. And if you visited the whole string and the last node that you visited was a node with its end of true, you return true at that point. Now please pause this video and try to write down implementations of insert and search in C++ and Java using the structure that I've just shown. Let us now talk about implementation of search function. So search function takes a string as an argument, which is the key that you are searching, right? This is in C++ and this is in Java. And this function returns a Boolean value. It returns true if the key is present in the trie and returns false if the key is not present in the trie. For example, if you have trie like this and if you're searching for BAD, then this function would return true. And if you're searching for a string which is not present in this trie, like if you're searching for a word like GEE is not present, it would return false. And if you're searching for GEEK, then it will return true, right? So its return value is true. This function simply follows the same steps as we have just discussed. It begins with the root of the trie and begins with the first character of the string. It traverses all the characters one by one and also goes level by level down in the trie. At any movement, if it finds that it cannot go further down because the corresponding child is null, it returns false, right? And if it could reach all the levels down and it could reach the last character of the string, then it checks finally whether the node at which we are currently at the end of the string, does it contain end of word as true or not. If is end is true, then it returns true, otherwise it returns false. So that's what we've done in both the codes. We have a current pointer or a current reference which begins with the root and we begin with the first character of the string. We traverse through all the characters. Now we need to find out index in the child array for the current character. So here I am assuming again that we have 26 possible characters of lowercase alphabets. So I am getting the index by subtracting the ASCII value of A from the current character. Right? That's how I get the index. Similarly in Java, I subtract the ASCII value of A from the character at index, given index, right? That's how I get the ASCII value. I use this index in the child array. So for B, I'll have the index as 1. For C, I'll have the index as 2. For D, 3, E, 4, and so on, right? And using this index, we figure out, do we have a child null? If we have a child null, we return false. If we do not have child null, we simply go down to the next level in our trie, right? We simply go to that particular child. And at the end, if we have traversed through the complete string, if this loop is over, we did not find a null child at any point, we come out of the loop and we simply check the node, the last node which we traversed, does it contain is end as a true value or false value? If it contains true, we simply return true. If it contains false, we return false. That's the simple implementation of search function. Now, please pause this video and write down a function for insert. You just need to make few modifications to this search function and you will be able to write insert function. Basically, the structure of insert is going to be very similar to search. There also we are going to traverse through all the characters. It is just that the return value is not going to be true or false. It's void and we are simply going to insert a key. Here are C++ and Java implementations of insert function. I have highlighted the changes with search function. So now we have a return type void. This function also takes a string as a parameter and simply inserts this string into the trie, right? And what it does, it traverses through all the characters of the given string one by one, right? In Java also we have a loop. And this is similar to search function. And it also begins with the root and traverses down the level one by one. The difference here is, if it does not find a child corresponding to the current character, instead of returning false, what it does, it creates a child. It creates a child for that particular character, right? We create a new node if we do not find a node for this particular character. And at the end, when we have traversed through all the characters of the given string, we must be at the node corresponding to the last character. So we mark is end for this particular node as true, right? That's what we do at the end. Let's try inserting a string into this try to go through this insert function. Let us now talk about time complexity analysis of insert and search functions. In the analysis, I am going to assume that alphabet size is constant. Alphabet size here is 26. We are considering 26 possible characters in every string that we have. If we consider all the ASCII values, then it's 256, which is also a constant. Let's now analyze insert first. What are we doing in insert function? We are traversing through all the characters of our input string that we want to insert, our input key. And for every traversal, we are doing a constant amount of work. We are doing a subtraction, then a lookup for that particular child, then a new node memory allocation. And new node memory allocation is also a constant work if we consider 26 as a constant, because we just create an array of size 26 and initialize this array as null. Then we are moving to the next child, which is also a constant operation, right? So all this is constant in every iteration of this loop for every character. So we have theta n work for insert for a key of length n. Let us see search function now. In search, we had similar structure. Instead of this, we were returning false if we were finding a null. So search is again big O of n. I'm saying big O of n because it may take less than key length if we do not find, for example, first character itself. So the search is big O of n, where n is the key length, and insert is theta n, where n is the key length.